if we are going to use these equations, these integrals, to determine the deformation and the rotation of beams, then we're going to be introducing quite a few constants of integration. Integrating, what, 4 times? So, we're going to need to think about what the boundary conditions are for these equations. We've already gone through the shear and the moment diagrams relatively extensively, I think. But for the rotation and the deflection equations, we're going to have to do some more. So let's consider these 2 examples right here. They've got pins, hinges, and free ends and internal bits for us to think about. And let's not worry exactly about what in particular the values are, but let's look at these and look at what it more or less is going to look like, and consider our boundary conditions. For this first one, we're probably going to look a little bit, there it is, undeformed, and the deformed shape is probably going to look a little bit like this, because at a pin, which we have at this point, or a roller, which we have at this point, so pins and rollers, the deflection must equal 0. Rotation, however, clearly there is some rotation right here, some rotation right here, and some rotation right here. These rotations are, well, equal. So the rotation at these points is going to be continuous. It's going to be the same just to the left as it is just to the right. A differential distance, of course. Not a significant distance. It's going to start tapering down. It's a function of x. Let's look at that free end. At a free end, like we have there, clearly there is some deformation. So the deformation, that's going to be continuous. I'm just going to write con for that. Ditto the rotation. There isn't a ton of rotation shown there, but there is some. So the free end gave us a lot of information about the constants of integration when we were considering these 2 equations, right? We can't have any internal moment, we can't have any internal shear at the free end. We can have rotation at the free ends, and we can have deflections at the free end. The pins and rollers, though, are going to just need to be a 0 for the deflection, and just continuous with the rotation. Now let's consider this beam. How do we think this beam will deform with that hinge right there? Let's draw it straight in black with that, and I'll draw the roller right there. Well, we're pushing down on it right here, so it's probably going to be down. We're going to probably have something like that. The rotation here has to be constant on this side and this side. But the hinge is just going to bend up. Right, okay, I drew the hinge. There's a little bit to the right of where it ought to be. It should be just above this hinge, because, and this fixed end. At a fixed end, both the deflection and the rotation have to be 0. This isn't going to allow any rotation at this point. At an internal hinge, the deflection has to be continuous. Right, the deflection at this point, just to the left of it, is the same as it is just to the right of it. But the rotation, oh dear, is discontinuous. Okay, there's a sudden change in the rotation. Okay, so these points, at this point we would have had a moment be 0. We've got a sudden change in the rotation, but the rotation is going to be non-zero, potentially. And the deflection is not going to suddenly change, but of course its slope does change. Its slope is the rotation.